You have never experienced a moment moving backward. Not once. Not even briefly. From the first second of your awareness to this exact moment, every experience you have ever had has arrived in the same order. One thing after another. Always forward. Always in the same direction. The past behind you. The future ahead. The present. The only place you have ever actually been. This feels so obvious, it barely seems worth saying. Of course, time moves forward. That is what time does. That is what time is. The question of why it moves forward feels almost meaningless. Like asking why up is up or why here is here. It is simply the nature of things. And yet, the laws of physics. The equations that describe how matter moves, how energy behaves, how particles interact at the most fundamental level, do not require time to move forward. They are almost entirely indifferent to the direction of time. Run them forward, and they describe a universe we recognize. Run them backward, and they describe a universe that is equally valid, equally consistent, equally permitted by the mathematics. The equations do not care which way time flows. They work in both directions with equal precision, which means the direction of time, the thing you have never once experienced being violated, is not written into the fundamental laws of reality. It is something else, something that emerges from the universe's history rather than its physics, something that could, in principle, have been otherwise, and nobody has fully explained why it isn't. That is the question this video is going to follow. Not loudly, not dramatically, but carefully. Because the answer, or rather the shape of the answer, since a complete answer doesn't yet exist, is one of the most quietly unsettling things in all of science. It suggests that the most basic feature of your experience of reality is built on a foundation that the universe had no particular reason to construct, that the direction you experience as inevitable is in fact contingent, that things could have been arranged differently, and that the reason they weren't arranged differently is a mystery that reaches all the way back to the first moment of existence. Let's start with the physics and what it actually says. There are four fundamental forces in nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each one is described by a set of equations, and for three of them, gravity, electromagnetism, and the strong nuclear force, those equations are perfectly time-symmetric. If you filmed any process governed by these forces and played the film backwards, the reversed process would be just as physically valid as the forward one. A planet orbiting a star in reverse is still a planet orbiting a star. An electromagnetic wave traveling backward through time would still satisfy Maxwell's equations. Two particles exchanging a strong nuclear force interaction in reverse would still be two particles exchanging a strong nuclear force interaction. Nothing in these fundamental descriptions of reality points an arrow at time. Nothing says this way and not that way. The mathematics is equally comfortable in both directions. There is one exception. The weak nuclear force, the force responsible for certain types of radioactive decay, is not perfectly time-symmetric. Experiments with particles called kaons and b-mesons have confirmed that the weak force behaves slightly differently depending on the direction of time. This violation of time symmetry is real. It is measured. It is called CP violation, and it is one of the most interesting anomalies in particle physics. But here is the crucial point. The asymmetry produced by CP violation is extraordinarily small. It affects an extremely narrow class of particle interactions, and it cannot by itself account for the overwhelming, universal, all-encompassing directionality of time that you experience in every moment of your life. The arrow of time that governs everything from the cooling of your coffee to the aging of your body to the expansion of the universe cannot be traced back to the slight asymmetry in kaon decay. The scales are incomparable, so the fundamental laws of physics, with one small and insufficient exception, are indifferent to the direction of time. And yet time has a direction, a powerful, universal, inescapable direction that has never once been violated in any macroscopic process anyone has ever observed. That gap between the time-symmetric laws and the time-directed universe is where the mystery lives. This is where entropy enters the story. Entropy is one of the most important and most misunderstood concepts in all of physics. In its simplest form, entropy is a measure of disorder, a measure of the number of ways a system can be arranged at the microscopic level while still appearing the same at the macroscopic level. A gas filling a room has high entropy. There are an enormous number of ways to arrange the individual gas molecules while still producing a room full of gas. The same gas compressed into one corner has low entropy. There are far fewer ways to arrange the molecules while keeping them all in the corner. The second law of thermodynamics states that the entropy of a closed system tends to increase over time. Disorder tends to increase. Organized structures tend to become less organized. Energy tends to spread out rather than concentrate. Ice melts. Coffee cools. Buildings crumble. Stars burn out. The direction from order to disorder, from low entropy to high entropy, is the direction we call forward in time. And here is where the arrow of time appears to come from. Not from the fundamental laws, which, as we've established, are time-symmetric, but from the second law of thermodynamics. From the tendency of systems to move from less probable states to more probable ones. From the overwhelming statistical bias toward disorder that emerges from the sheer number of possible arrangements of matter and energy in the universe. Think about it this way. If you drop a glass and it shatters on the floor, you never see the shards spontaneously reassemble into a glass. Not because the laws of physics forbid it, they don't. The fundamental equations of motion are perfectly compatible with the reverse process. But the number of ways the molecules of a shattered glass can be arranged in a shattered state is so vastly larger than the number of ways they can be arranged in an intact glass that the probability of spontaneous reassembly is not zero, but is so close to zero it will never happen in the lifetime of the universe. The arrow of time in this picture is a statistical arrow, not an absolute one. The laws don't say time must move forward. They say the universe is almost certainly going to move from less probable states to more probable ones. And since more probable states are more disordered, and since we call the direction of increasing disorder forward, time appears to move forward. This is a profound and genuinely strange thing to sit with. The direction of time, the most fundamental feature of your experience of reality, rests not on an absolute law, but on a statistical tendency. On the fact that there are more ways to be disordered than ordered. On the fact that the universe is playing the odds. But here's where the story gets deeper, and where the unease shifts from physics to something more personal. Enter memory. You remember the past and not the future. This seems obvious. This seems like the definition of what past and future mean. But it is not obvious at all once you understand the thermodynamics of information. Memory is a physical process. When you remember something, you have a low entropy record, a specific, organized arrangement of neurons that corresponds to a past event. The record exists in your brain as a physical structure, and that structure was created by the event it records. Why does memory point backward and not forward? Why do you have records of the past and not the future? Because creating a record, any record, mental or physical, requires increasing entropy. The process of encoding information always generates disorder somewhere in the system, which means the direction in which records can be created is the same as the direction in which entropy increases, which is the direction we call the past. In other words, you remember the past and not the future, not because time flows forward, but because the thermodynamic arrow of entropy points in one direction. Memory is an entropy phenomenon. The feeling that time has a direction, the felt sense of moving from past to future, is in large part a consequence of the fact that your brain is an entropy-generating information processing system embedded in a universe of increasing disorder. Remove the thermodynamic arrow, and memory loses its direction. Remove the direction of memory, and the felt sense of time moving forward dissolves. The experience of temporal direction, the most intimate and immediate feature of your existence, is downstream of thermodynamics. That is either deeply elegant or deeply unsettling, depending on how long you sit with it. But here is the question that this entire chain of reasoning eventually arrives at. The one that the physics cannot answer. The one that sits at the bottom of everything. If the arrow of time comes from entropy increasing, and if entropy increases because the universe is moving from less probable to more probable states, then the arrow of time ultimately depends on the universe having started in a state of extremely low entropy, a state of extraordinary order, a state so improbable, so precisely organized, so far from the maximum disorder that the universe will eventually reach, that the entire subsequent history of increasing entropy, the entire arrow of time from the Big Bang to the heat death of the universe, flows from that single initial condition. The universe began in an extraordinarily low entropy state. That is not controversial. The evidence is in the CMB, in the large-scale structure of the cosmos, in the very existence of stars and galaxies, and the organized complexity they make possible. The early universe was far more ordered than the universe will eventually become, and the direction from that early order toward the eventual disorder is what we call the arrow of time. But here is the question. Why did the universe start in such a low entropy state? This is where the physics runs out. Not partially out, completely out. The second law of thermodynamics explains why entropy increases going forward from any given initial state. It does not explain why the initial state was so extraordinarily ordered in the first place. That initial condition, the low entropy beginning, that the entire arrow of time depends on, is simply assumed in our standard cosmological models. It is put in by hand. The models take it as given and derive everything else from it, but they do not explain it. Physicist Roger Penrose has spent decades trying to calculate just how improbable the initial low entropy state of the universe was. His estimate, derived from the mathematics of gravitational entropy and the geometry of the early universe, is a number so extraordinary it is difficult to write down. The probability of the universe beginning in a state as ordered as the one it apparently began in, if you were to choose an initial state at random from all possible states, is approximately 1 in 10 to the power of 10 to the power of 123. That is not a number that conveys meaning through reading. It is a number that conveys meaning through the fact that it exists. It is saying that the initial condition of the universe was not just improbable. It was improbable in a way that makes the concept of improbability feel inadequate. Why was the universe so ordered at the beginning? Why did it start in a state that made the arrow of time possible? Possible answers exist. Inflation produces a certain amount of homogeneity in the early universe. Some theorists propose that the low entropy beginning is connected to the multiverse, that in an ensemble of universes with random initial conditions, the ones that produce observers necessarily have low entropy beginnings, because high entropy beginnings don't produce the conditions for life. Others propose that the initial condition requires a deeper explanation that current physics cannot provide. None of these answers is complete. None of them fully explains why the universe began the way it did. The question of the low entropy initial condition is one of the deepest open problems in cosmology. And since the arrow of time depends entirely on that initial condition, the question of why time moves forward ultimately rests on a foundation that nobody has yet explained. You experience time moving forward in every moment of your life. Every memory you have, every anticipation you feel, every sense of before and after. All of it flows from the fact that the universe happened to begin in a state of extraordinary order for reasons that physics has not yet determined. The direction that governs everything you have ever experienced is built on a foundation that science cannot yet account for. And the most honest thing that can be said about it is also the most quietly unsettling. We do not know why the universe started the way it did. We do not know why time has the direction it has. We have traced the arrow back as far as it goes, back to the first moment of existence, back to an initial condition of improbable order. And there we find not an answer, but a deeper question. Why this beginning and not another? If you are drawn to the questions that refuse resolution, the ones where following the logic carefully leads not to answers, but to better questions, then Cosmora is exactly where those questions live. Subscribe and stay. The ones ahead are stranger still. But before we close, here is the thought that belongs to you now. Every moment you have ever experienced has arrived in order, one after another, always in the same direction. You have taken this so completely for granted that the question of why it happens this way has probably never occurred to you until today. And now that it has occurred to you, now that you understand that the direction of time is not written into the fundamental laws, that it rests on a statistical tendency toward disorder, that it depends on a memory effect that is itself thermodynamic, that it flows from an initial condition of extraordinary improbability whose origin physics cannot yet explain. The forward movement of time looks different than it did before this video started. Not terrifying, not incomprehensible, but different. Less like the furniture of reality that was always going to be there. More like something that happened to be arranged a certain way at the beginning. Something contingent. Something that rests on a foundation of extraordinary, unrepeatable, still unexplained order that existed once, at the start of everything, and has been unwinding ever since. You are living in the unwinding, moving through time in the only direction the unwinding permits, and somewhere at the bottom of why that direction exists, and not some other one, there is a question that the universe has not yet answered. Maybe it never will. Or maybe the answer is waiting in the direction we haven't learned to look yet.